Well, I've moved the 570 to a new home. I may show you that in a minute, but basically it's the workbench that I did some time ago called the Vintage Radio Workbench. It's just a workbench in my garage. And this is, I think, going to be the permanent, or at least for now, permanent home of the 570. And what I look forward to doing is carrying out a series of experiments. What you see on the screen is a 7N7 medium U twin triode. Now the reason that I'm showing this is when I was doing the 6SN7, which is also a medium U twin triode, I mentioned that I would compare it with a 7N7, which is a Loctal equivalent. Now, a Loctal tube, let me show you one here, has a somewhat unique look to it. Instead of, it's an 8-pin, just like an octal, but it has, its center pin has a little locking ring. And as I mentioned in a previous video, most people speculate that this tube really wasn't needed. It was just invented to get around the patent restrictions on the octal type socket, so Philco wouldn't have to pay royalties. But that aside, the 7N7, this medium U twin triode, is essentially the same as the 6SN7, except it has the Loctal socket. Now you may wonder about the 7 instead of a 6. Isn't that a 7-volt tube? No, actually, because the 6s were already used up, and because Philco wanted to preserve as much of the numbering as they could, what they did is they just went to the next higher number. So this is unique. Even though it says 7, it's really a 6-volt or a 6.3-volt tube. So what they did is they took a 6N7 and put it in a Loctal base and called it a 7N7. So this is the display of a 7N7. Notice that the two sections look pretty close. That's section A, B, A, B. Okay. Now what I'm going to do is set up to test the 7N7 on grid A and the 6SN7 on grid B, and let's see if there's any difference. Okay, now what we have is I think I need to find a way to get rid of some of that glare. Well, I'll work on that off camera. This is one section of the 7N7. Get it back on the baseline. It does drift when you turn it off for a while and then turn it back on. So that is the 7N7. That's the 6SN7. Essentially identical. That's one section of a 6SN7. Let me see if I can turn the camera down here and show you what I'm running here. On this side is a 7N7, and it is using that Loctal to octal adapter that I talked about in a previous video. And then over here is a 6SN7, and the only difference between an SN7 and a 6N7 is this is in the S means short. It's in this short octal style. The 6N7 was a glass, or was a metal tube, exactly like this, except with a metal case. So now let's come back up and look once more at the now that glare has gotten worse. I don't know anyway. 6SN7, 7N7. So I thought you might be interested in that, partly because I talked about it in a previous video. I'm going to be going on and doing some more experiments using the 570. So I may add those to the end of this video, or I may just post this as a little short follow-up to the previous two. Earlier I said that a 7N7 is just a 6N7 with a loctile base. That's wrong. What I should have said is a 7N7 is a 6SN7 on a loctile base. Let me show you why I say that. If you look at the 7N7, you'll notice that it is a true dual triode. In other words, each section is completely separate. You can control the cathode, the grid, and the plate of each side of the tube independently. But that's not true of the 7N7 or the 6N7. Notice with the 6N7 that the cathode is shared. In other words, there is not a cathode for the left triode and a cathode for the right. There is a common cathode. So let's compare that now with a 6SN7. On the left is a 6N7. On the right is a 6SN7. Notice that the 6SN7 has separate cathodes. And as I pointed out, the 6N7 did not. It had a common cathode. So that's an important difference, because if you try to use a 6N7 in an application where the cathodes are not tied together, it will not be able to perform correctly. Whereas a 6SN7, you can treat each triode as a separate tube. Now, I should have noticed that. Frankly, I didn't notice it until after I was reviewing the video that I made. But if you look at the 7N7, it says specifically that it is similar to the glass octal type 6SN7 GT. So I let myself be tricked by once again, by the fact that Philco kept the N7, and instead of calling it a 7SN7, which would have been more correct, I think, they called it a 7N7. So why do I do all of this? Well, a lot of people are beginning to use 7N7s in audio amplifiers because these 6SN7s, like over here on the right, are getting extremely expensive. The new old stock 6SN7s, some of them can run you more than $100 per tube, whereas 6N7s, I'm telling you wrong. Once again, 7N7s are fairly readily available. So they are much cheaper. Now, they're still not cheap, but you can replace a 6SN7 with a 7N7, but watch out for a couple of differences. One is, of course, that this is a loctile base instead of an octal. But there's another thing that you may notice, a subtle difference as well. On this one, the heater is between pins 1 and 8. On the 6SN7, the heater is between pins 7 and 8, not 1 and 8. Also, many of the other electrodes are numbered differently as well. So, for example, pin 2 is the plate of a 6SN7, whereas it is the cathode of a 7N7. So you can't just use the adapter plug that I told you about earlier to plug one of these into a socket wired for one of these. You have to rewire the socket, or you could build the adapter so that it automatically makes the appropriate cross connections. And I think I saw, I don't remember quite, but I think I saw some on the internet where you can buy adapters where these necessary cross connections are made. For example, pin 1 of the 7N7 has to go where pin 7 of the 6SN7 was, and you can figure out the rest of it yourself with a tube manual. So at any rate, maybe I've beaten this horse way beyond its death, but I did want to correct that earlier error. What you see now is a 6AU6 PenToad being displayed. I am still using a 100 volt DC potential on the screen grid, and the and 100 or 200 volts peak, that is 100 volts in the center, 200 volts on the right, peak, with a 10K series load resistor, which is basically the slope that you see here and I talked about in a previous video. What I want to do now is to convert this from a PenToad to a Tetrode. And the way you can do that is, the difference between a PenToad and a Tetrode is PenToad has 5 elements. It has a suppressor grid, which is normally connected to the cathode. What I'm going to do is move the suppressor grid from the cathode to the screen grid. And you notice what happens. This big dip is what was known in the day as the Tetrode kink. What happens is, I'll talk a little more about this in a minute when we take a look at the 6AU6 itself, but now I'm going to move it back to the cathode, and you notice in this case it's operating as a PenToad. A minute ago I was operating it as a Tetrode. So let's talk a little more about that. So here is the tube that we have been looking at, the 6AU6. Notice it's titled a sharp cutoff PenToad, and this was primarily used as an RF amplifier. It was used in some radios, but especially in television sets of the 1950s. Better tubes came along, and of course transistors, especially field effects, pretty much made all of this fairly obsolete, at least in RF applications. But this is the PenToad that we have been working with. Let's take a closer look at the PenToad structure and also at how it's used in a circuit. So this is a PenToad, and the notice that it has some new terms. If you've only been looking at triode tubes, that'll look a little new to you. Of course, you'll recognize the grid, the cathode, and the plate. But in addition, you have a screen grid and a suppressor in a PenToad. Now in a minute we will look at a Tetrode, which actually preceded the PenToad, and we'll talk about why it was developed the way it was. But normally you'll notice the suppressor grid is connected to the cathode. That's this connection right here. The screen grid is connected to a positive voltage. And for reasons that we'll look at in a second when we look at the Tetrode, you generally want the screen grid to be a positive voltage, but to remain at or below the plate voltage. Well, of course, as you know, in an amplifier, the plate voltage is varying. So you would like the screen grid to stay at the minimum of the plate voltage. the higher the screen grid voltage is, the more gain the tube will have, but there's a little problem with what's called secondary emission. So let's first look at a Tetrode, and then we'll come back to the PenToad. One of the things that engineers realized when they first started trying to build RF amplifiers with triode tubes was the capacitance from grid to plate caused a problem. It's called the Miller effect because he studied and published a lot about the effect. Basically, the plate is one side of a capacitor and the grid is the other side. And the signal that appears on the plate is coupled back to the grid through that capacitor. And that's negative feedback, which reduces the gain of the stage, and it got worse as the frequency got higher and higher. So one of the things that electron tube designers decided to try was to put a screen between the grid and the plate to screen the grid from the effects of the plate changes. In other words, to effectively reduce the grid to plate capacitance. And they connected that screen to a positive voltage. The idea was that it would attract the electrons through the tube, but because it could be bypassed, and usually there was a capacitor from the screen to the cathode to bypass the AC signals, so that basically for AC the screen was at the same potential as the cathode. Well, that reduced the grid to plate capacitance by a factor of, in many cases, several hundred and maybe as much as 1,000. So for example, a 10 picofarad capacitance between grid and plate might be reduced to a 10 nanofarad capacitance. Now, I'm using modern day terms. Back in the day, they would have called it microfarads, but I'm using modern capacitance terminology. But one of the problems they ran into was with the screen is if the plate voltage drops below the screen voltage, secondary electrons that bounce off of the plate or are driven off of the plate by the stream of electrons flowing to it collect near the plate, and they are attracted to the nearest positive voltage. Well, if the screen voltage is slightly more positive than the plate, they will flow to the screen and down. And the problem with that is it produces a unique characteristic in the plate characteristics of the tube. Let's look at that. Here is an example of what's called a screen grid RF amplifier. It's an RCA 24A, and this have been used in radios in the 1930s, at least early in the 30s. It did solve some of the problems with the inter-electrode capacitance, reducing the Miller effect greatly so that you could get much higher gain at higher frequencies. But, as I pointed out, if the screen winds up slightly more positive than the plate, you get what's called secondary emission and screen current. And let's take a look at what that does to the characteristics. Here you notice that they have drawn a line that shows, and for this case, this is the plate characteristics with plate voltage where the screen voltage is set to 90 volts. Right here it says screen volts equals 90. So at 90 volts or less, notice it says values unstable. And that's because the secondary emission flowing to the screen causes the plate characteristics, basically the plate current is diverted down to the screen grid, so it doesn't show up on the plate. Once the plate gets more positive than the screen, then it operates as like a PenToad. But this kink in the characteristics it was undesirable. And that is why that pentodes were developed with a suppressor grid. It got that name because it suppressed the effect of secondary emission. And so that is how the pentode began to be developed. After the development of the pentode, very few tetrodes were ever built. The reason is the pentode, as we showed a little bit ago on the 6AU6 pentode, you can turn a pentode into a tetrode by simply connecting the suppressor grid to the screen. But you achieve all the advantages, and it basically gives you a high gain, high frequency tube with very low grid to plate capacitance and no kink. By the way, if you're an aficionado of audio amplifiers, you know that there is a line of tubes that are labeled KT. The KT stands for kinkless tetrode. The reason is, basically what they did is they solved this problem another way, not using suppressor grids, but by using what are called beam power tubes, which a beam power tube is built like this. Not only is the screen grid and the control grid lined up, that is, so that they are on exactly the same plane from top to bottom, that causes the electrons to flow in sheets, but also two beam-forming plates are placed, one on each side, that serve as the suppressor that push the electrons into a very narrow beam. They hit the plate, and basically the idea is it's almost like trying to go upstream in a fire hose. If there's a huge flow of electrons and an electron bounces off or is emitted by the plate, it gets swept up by that electron flow and driven back to the plate, so it does not wind up back on the screen grid. And this was called a beam power tube, and in Europe they tended to call them kinkless tetrodes. One further thing that I wanted to talk about with respect to the 570 is the fact that it only has one heater voltage. Now, the heater voltage is set with this control right here, and it has a wide range. In fact, it even has an adjustable so that you can set to values that are right on or a little below or a little above the nominal heater voltage. And that's wonderful if you're using two tubes that have the same heater or the same heater voltage. But there are times when you cannot do that. For example, suppose you're comparing a 12-volt tube to a 25-volt tube. Well, in that case, you need to set you need two heater voltages. You can use the Tektronix heater voltage for one of those tubes, but you need a way to generate a heater voltage for the other one. And I've come up with a solution that consists of an octal socket plugged into a tube tester with a pair of plug leads that this is the filament voltage on this, and I'm only using this tube tester as a filament transformer. I'm not using the meter or any of the other parts of it, just the filament transformer. But you can set the filament voltage using the normal settings here, and instead of plugging the tube in here, you use these and you plug them in to the appropriate heater connections for the tube you are using. So I thought I might show you that as a kind of improvement to the 570. It would have been nice if they would have provided a way to select two different heater voltages, because you certainly could run two different heaters off the same transformer inside the 570. But rather than try to rewire the 570 to do that, I decided to use this sort of, well, let's just say field expediency of building an adapter for an old tube tester and use that tube tester to supply the second filament voltage. So I hope this has given you an idea of the 570 and some of its capabilities and how you can play around with tube characteristics, looking at differences between pentodes and tetrodes as I just did, comparing one tube with another, comparing two sections of the same tube to see how well matched they are, things of that sort. The wonderful thing about the 570 is not only is it a classic piece of test equipment, but it's Tektronix quality. I mean, this was the heyday of the Tektronix company, and they built the finest equipment in the world. So I am very, very happy to have this 570. I know I'm going to have a lot of fun with it, but I think for now it might be a good time to close things down a little bit, at least on the video side, and wish all of you a nice day.